and thank you very much for having us here in the wonderful country of Brazil, Sao Paulo. We're going to talk a bit about how we can use structure optimization to help the climate. But before I go into that, maybe just a short note on where we are coming from. So here we have the world, and this little circle at the top of the north, at the south of Scandinavia, that's Denmark. So that's where we're from. And our university is located in our capital. So I guess the whole of Denmark is what, one-tenth of Sao Paulo state. So it's a small place. But anyways, our university located here in Copenhagen, you can see the campus. It's only polytechnics. So we have around 13,000 students. We are around 2,000 scientific staffs. And then we have a revenue, which I translated into real, so it made more sense to you instead of Danish kroner, around 4 billion. So that was enough about where we are from. And of course, you're more than welcome to come join us in Denmark whenever you have the time. Okay, so the DTU top-up group, some of our selected results, we do stuff on different scales, different physics, all kinds of fun stuff. So from the top right, you have some gigascale structures, which is what I'm going to talk about now. And then we go into structural hierarchy, multi-scale structures, and medical implants, into photonics, microacoustics for medical devices, heat exchangers, which Kasper will talk quite a bit more about, and into nanophotonics and other kind of thermal problems. So basically anything where you have a macroscopic description of the physics, we go in, tweak the parameters, and change the design. And what do we mean with changing the design? Well, lots of methods exist to do that. You could do shape optimization, you can do sizing optimization, you can do topology optimization. And one way of thinking of topology optimization is like this, that you just take some domain and then you ask every point in space, do you want to be material or do you not want to be material, such that we get the best performance possible that we're after while fulfilling a number of constraints. And you can do that in a number of ways. The way we're doing it here, at least for the stuff I'm showing in this presentation, is we use continuous variables. And then we minimize some functional, could be maximizing stiffness, could be whatever, and we have a series of constraints. So of course, you need to solve this mathematical programming problem, and you need to include a number of other features. You need some good interpolation to ensure that you end in some physical design and that you can interpret grayscale if you have it. You could even project your way out of it. You could do geometric control, manufacturing control, and all these kind of things. So it might look like a difficult thing to do, but the nice thing about topology optimization and why it has become such a popular tool is that whatever you do, it always looks like this, basically. You initialize your model, you do some analysis, use finite elements, finite volumes, whatever you want to do, then you perform sensitivity analysis. And that's really the key to the success of this whole deal. I mean, the ability to have, of course, it only works with a few constraints, right? But if you have a few constraints, you can use the adjoint method, really efficiently get the sensitivities of many design variables, and then you do some regularization. Again, you can do many types, could include geometric filters for manufacturing, and then you redistribute material by some optimality criteria. So here again, switching from BESO to OC to MMA, second order methods, take the weapon of your choice, not a problem. And then you stop when you're happy, or if you reach a KKT point. But since we're all engineers here, we don't care about KKT points. So just to prove how sort of simple this is, you can actually put it onto an app. So you can make interactive 3D topology optimization on an iPad or on a phone or on a Windows computer as here. So we start out designing a hanger, then we change it to a suspension deck or suspension bridge. Then we watch the geometry unfold, and then we decide we want to do a top deck bridge instead. So we simply just move it up. And interactively, you can see the geometry changing and progresses as we go along. Of course, this is for educational purposes. This is not something you could use to build bridges in the real world. You can do it for toys. So if you have small kids, you can get them to print with your favorite glue printer, and you can put them in their dollhouses, and everybody's happy. So we've made a number of these apps, some together with colleagues. So we have 2D, 3D, combined shape and topology optimization, a finger finite element app we did together with Simulia. So you can draw with your finger, and then you can tweak it, let it go, and watch the dynamics happen. So that's all fun. And that was just the background of where we are. And I hope I haven't spent too much time yet, because now I'm getting to what I wanted to talk about. So I'm going to start with a story from industry and 20 years ago. So I'm going to talk about how we can reduce fuel consumption in aerospace. So my story to start off with is the design of the A380, which was completed in the early 2000s. What Airbus did when they did it, and you might be able to see it just by looking at it, they took the A320, the money cow, and they just stretched it. And then they told, before having built it, they told a lot of people who buy aircraft, it flies with this much fuel per whatever mileage. And then everything was happy. They got a lot of orders. Then they built the aircraft. Then they took it for the test flight. And they realized that they couldn't meet the fuel economy, which is a problem if you've promised it and you are a real company and not a university. So what Airbus did was they told all the design departments, reduce weight, because that's the easiest way to reduce fuel economy or fuel consumption. And one of the groups, they consist of around 40 engineers, they work only on this small part of the wing, the leading edge. So what they did was they took every rib out, removed the material, did the topology optimization thing, which is to non-mechanical engineers, no round holes, not good for stressors. So they did a discretization and they started the optimization process. And as you see, out of nothing comes definitely not round holes, but a nice structure, which consists of some configuration of straight bars, best for transferring loads in tension compression, no moments. And then they took a block of aluminum. You can see these are big, so 2 meters times 1 meters. And then they milled out 95%, repeated the process for every guy of this. And by doing this for the entire aircraft, they were able to meet the fuel consumption that they had promised. So that's a success story, but it also raises the question of what happens if you look at the whole thing? I mean, taking a little part out of the big part, of course, you're not being holistic anymore. So what happens to the rest of the aircraft when you touch one of the small things? And we all know this if we know about stresses, right? If you have a problem where you have high stresses one place, you can change the geometry up here, and that will do something about the stress level at a completely different place. Okay, so coming from Denmark, put it like this. These are Legos. These are the ones we played with when we were small, but we want to play with the real Legos, the fun ones where you can get some nice details. So we call this gigavoxel morphogenesis, and well, honestly, we didn't, but we had to give it a name that wasn't topology optimization, because apparently topology optimization is not a sexy name. But I don't know. So let's take that politics aside. Okay, so overcoming this problem, what could we do? Well, we start with the wing, an entire wing of an aircraft. So the goal is, of course, to reduce the weight so we can get less fuel per mile. Okay, so this is a big aircraft. Me and Kasper just landed with one of those yesterday. So you can see here we have a wingspan around 27 meters. And we now want to extract all the geometry on the inside. So what we did is we did a mapped mesh. So we have a finite element model. And we then asked, with the best software we had available at the time, what kind of details can we actually resolve? And we did some of our own codes and we did some with commercial codes. And around 5 million 3D linear hex elements was what we could work with. But then you get details of around 5 centimeters. And of course, 5 centimeters, if you pull off the skin of an aircraft wing, then you will see that's not representative. They need to be much smaller. So we found if we reached over 1 billion finite elements, we were able to get a maximum element size of 0.8 centimeter at the very root of the wing and sub-millimeter at the tip, because we're doing this mapped mesh. We decided that's enough, and we argue that that's a good enough reason to go into giga resolution. Okay, so next step is, of course, to figure out how do we capture the real physics. We need some load data, some support data. And the nice people from NASA were capable of producing this for us. We asked Boeing, we asked Airbus, we asked a lot of people, and all said, no, we're not going to share that with you. But let's see what you find out, and then we can talk again. Okay, so of course, you have a lot of load cases. As you can see, I'm pointing into blindness. We have the load cases here on the flight. We decided by trial and error, checking which were the dominant ones. We ended up with choosing just a few, and also a load from the engine mount, and then support conditions, as you can see down here. I'm just highlighting this little slice because I'm show it later. Okay, and then we got to running the code. We just took all the algorithms, basically like the Airbus people did back in the days. We just took our code, like the A320 to the A380, and just see what happens if we went from 10 to 100 million elements to 1 billion. And of course, just like Airbus, our codes were not able to fly. We needed to do something different. Not fuel consumption, but basically we needed to figure out how to generate new solvers. We were using purely geometric-based multigrid preconditioners before. That was not good enough when you go into a couple of billion unknowns and you have this high contrast. We also had problems just looking at our results because, well, 2 billion unknowns, of course, leads to quite a bit of data. And we also need to look at how we did the optimization, because we don't want to run forever. I mean, this cost a lot of effort. and we need to do some load mapping and all these kind of things. So we spent a year on this. And then we had something that worked, but coming from Denmark, we don't have big anything. I will show you later. But we don't have anything really big, not even supercomputers. So we had to apply for money on a supercomputer in France over time, which we got, which is really nice. And just to give you an idea of the results I'm going to show next, if I had run it on a single CPU, it would have taken 100 years. But we did it on 6,000 or 8,000. Actually, I'm not totally sure. And that was in 2015, we did this study. If we're doing it today with our updated algorithms, we can cut it to 1/3. So now we can do the same in 30 years on a single one. But you might be thinking a little bit about electricity here, because supercomputers are definitely not green. You can find this green 500 list of supercomputers, but it doesn't mean they're green. It just means that they use less power than others. Okay, so I'm going to come back to that hopefully at the end of the talk. But for now, let's look at the physics. So what comes out when you do this optimization? So this is the airfoil, which we have opened up like a fish, cut it in two, flipped it upside down, and you look at it. So what you see is definitely that you have some members that goes tens of meters. And if we zoom in at the tip, you will see details here, which are around 1 centimeter in diameter. So we are covering, 4 orders of magnitude. But you're also seeing a lot of interesting mechanics, actually. And we have to think a bit about this. So you see here, you have nice closed wall structures, and then you have these truss-like lattice structures here. And then it goes into another, truss, closed wall, truss, semi-closed again. And you can see the same features if you look at the root. You have this closed wall that goes into a truss and then closes again, and again down here. So of course we asked ourselves, what's that actually telling us? And that actually leads me to a good point. So this is around the time where 3D printing was really hot and everybody was doing crazy stuff. So I'm just showing, I'm not pointing fingers. This is not to put blame on these companies. I'm just saying these are the things that were presented back some 10 years ago. And they all said, this is the best designs ever because lattice structures provide optimal stiffness to weight ratios. Well, we are mechanical engineers, at least some of us. Not sure about you, all of us. But that's not true. That's a misconception. In fact, they are probably around 2 to 3 times less stiff than closed wall structures. So if you think about the design you saw before, and you like large-scale computing like me, what you're actually seeing is that we are doing 2 coarse measures. Because if we allowed, let's say we put in instead of 1 billion elements, we had 100 billion elements, we would, wherever we saw a lattice-like structure, we would see a thin closed wall. Okay, I can show this. So let's go back to the origin of our research field. So this is the paper by Michel did in 1904. Of course, he had to do anything by hand, which has the small problem that when he wanted to give a message, and I have read this, by the way, not easy reading, and I'm not English speaking, I'm not sure he was either, but you look at his design for this torsion sphere, and you think, optimal is a truss structure. This is what he draws. But what he actually writes is, he says, you need infinitely many of these, infinitely closely spaced. And if you have an infinitely closed truss member and infinitely many of them, then you have a closed wall. So how can you show that? Well, you can show it if you do a very fine mesh, such that you allow to capture the thin closed wall structure. So, where's my little, sorry, here. So in this, we did not put any length scale requirement. We just put a volume constraint. Here, we imposed a length scale, the same amount of volume. And you can see if we impose a length scale, it cannot produce this because it's too thin. And we get exactly what you would expect to see from this figure, but not the optimal. And you can see that again, if you look at the compliances here, that it's significantly less for the closed wall sphere. Okay, but what was gained? Back to CO2 emissions. So, of course, we could not get anybody to produce these guys in the real world, so we have to extract some features that representative. And one of them is that if you look, and this is the blue little area I showed you before, you can clearly see that our wing boxes are in fact curved, and which makes sense because they're expressing torsion or experiencing torsion. So we did a small study on that, pure analytics, and then we also took, so this is a regular layout of a divider of the wing, so you can have the fuel, so it's not going to fly around with 2 big bathtubs. Just divided that in a slightly different way. And what was changed? Wait a minute. Here, there it is. So just by these 2 features, not all the other fine stuff, we see that you get to a 2 to 5% weight reduction for the wings, which lead to around or up to 400 tons of fuel saved per year, which we thought was a lot, but apparently the A380 spends up to a ton just taxiing. So room for improvement if anybody want to go this direction. Let's see. Yeah, I should move on. So just some references to nature. Of course, what we're doing mimics quite a bit what nature does with evolution. The only difference is we use gradients, meaning we don't do a lot of offsprings and then kill off the bad ones and keep the good ones. We just take the good ones, and every step we keep taking the good ones. And you can see Airbus, they went back and then they liked what we did and they wanted to use it. But yeah, enough about that. So the thing is, as I told you, we don't have aerospace industry in Denmark. So when we did this study, we were hit on the head by our funders who said, well, interesting, but not interesting. Couldn't you look into civil engineering? And we were like, well, we're good. And we did. So we hooked up with Collouium, a big company who's producing large suspension bridges all over the world. So this is the bridge we're going to talk about, the Osman Gazi Bridge, which was built recently in Turkey. And this I've included because that little point up there, that's the highest point in Denmark. And the highest point, if you want to stand on soil, that would be around here. Actually, there is one point that's higher, but it's only going to be there at every certain frequency because we have a gigantic, I think it's 320 meter wind turbine. But of course, don't want to stand on the blade and definitely not the tip moving with 200 miles per hour or whatever. So best spot to get a view of Denmark if you can get up there. Okay, so what we're going to look at are the box girders that you can see here. So it's a repetitive thing to do these suspension bridges. You do the same thing, put it up and repeat it and repeat it and repeat it. So why is this interesting from an optimization perspective? Well, in the beginning, honestly, we didn't know. But then we talked to civil engineers and they told us, oh, this design was developed, completed in 1966. And we're still using it now, 60 years later. And I guess it goes without saying that 60 years, I mean, in the 60s, no big computers, no calculators, basically, no nothing. So, of course, there must be some room for improvement. So we said, well, if it's been used for 60 years, we can probably do something about it. So we went in, and I'm sorry, but I think I need to skip a bit. We did the same thing. We did a modeling domain. We decided on loading conditions. We did include some symmetry conditions. We had some passive domains. We ensured that everything fixed. This is our design domain shown here. This is our modeling domain. We had some loading conditions, 5 in total. It's a non-self-adjoint problem. So that means for every design cycle, we need to solve 10 PDs. And we did that. So again, here, 10 PDs solved per iteration, 5 load cases plus 5 adjoints. We did that for almost 6.5 billion degrees of freedom. And our code, now being severely optimized, gave us a PD solve time around 35 seconds per PD, by the way, for 2.1 billion elements on 16,000 cores. So we're back to this supercomputing thing. That's a lot of energy we're burning. And then, of course, you learn stuff. For example, we did not check timing on what it took to actually write restart files. And when we were done with our job, we found that we had spent almost a third or more than a third of our time writing to this. But I'm going to have to skip that. Let's see. There's the design. I'm not going to go into much detail, except this is not something you can get civil engineers to do. It's all struts and ties, something that resembles closed walls. So we actually did the same as we did for the wing. We looked at it and said, well, what's it telling us? Well, it definitely tells us that we should be using curved plates to connect the hangars to the deck. So we did that, did a subsequent sizing optimization on it, and then we did a comparison with the conventional design, the one that's in the Osman Gazi Bridge. And when we did that, we could see we could get almost a stiffness improvement of up to 30%, which translates into a weight reduction due to knock-on effects of up to 19%. So, of course, if you reduce the weight of the deck, the girders, you don't need as much concrete for the pylons. And concrete is one of the enemies. I mean, producing concrete is not a good thing for the environment. You need to heat up stuff, and you need to heat up bad stuff quite a bit. So that, for the bridge in question, that would translate into 43,000 tons of CO2 reduced. Of course, you could translate this into high rises. I mean, in your beautiful city, I think just within a radius of 500 meters from where we are, you'll find taller buildings that you'll find in the entirety of Denmark. But anyways, so lots of potential for doing some fun stuff here. Yeah. Okay. So to the final part. So we know we are burning diesel, gasoline, firing up these supercomputers, which is not good. So why not ask the question, could we kill this part? Could we go directly to high resolution, optimized designs without using supercomputing? And here the story becomes really funny, and especially for older people like me, because actually what we did to do this is to go back to the origin of topology optimization. So this is how it started, homogenization problem. You are optimizing density variable while you're optimizing the orientations of your laminations with a rank 2. So this is the result. And what you can actually see from this, if you are a somewhat skilled mechanical engineer, is that you could basically draw how the geometry should look. Like you can see the streamline, not the streamline, sorry, the principal stress directions and how they interact. And of course, you can do that by an optimization problem. You can solve an auxiliary optimization problem on a coarse mesh still, projected to a fine mesh. And here you have a fine scale solution, which looks really nice and has a good performance. And you can get a speed up of a factor of 102. And you can do the same in 3D, where again, so this is the SIP solution, which looks nice. This is the dehomogenized solution, which has some artifacts. I mean, this is not plug and play yet. We're still working on getting these methods better. But you don't lose anything, or at least you don't lose more than a couple of % from this. And all of this can be run on a standard single desktop computer. The only thing that cannot is the post-evaluation. Still need quite a lot of finite elements to do that. Okay, I'm getting towards the end. So now we're working at all kinds of different methods to do this dehomogenization, because as I told you, it pretty much looks like something you could draw on a piece of paper. You see the principal stress directions, you see the lamination width, you know how it's going to look. That sounds like computer graphics, right?
It's a novel method for generating multi-laminar structures, which has applications to topology optimization.
So this is
Initially, we trace a superset of stream surfaces that follow an input frame field. From this set, we choose a uniformly spaced subset of the surfaces by solving an optimization problem. Finally, we create a volumetric representation of the near-optimal mechanical structure.
Don't you just love automated speech?
Propose a novel method for generating.
I'm gonna have to skip from that because I can't hear it. So again, you could see we get something nice. Of course, we got a nice video because we're working with people in computer graphics and they know how to do nice graphics. But again, we're kind of improving on, We're kind of improving on the complexity. So we don't see these artifacts as you saw in the previous works. And you're losing a little bit of our compliance, but nothing much. Okay, and I think I actually made it, half a minute before. Some references, I can give you a PDF of this if you want it. And other than that, would be happy to take any questions you may have. End of talk. Okay.
Thank you. So let's open for questions.
About how performance the computer is on cloud or no? Supercomputer.
Not cloud computing.
Not cloud.
We have done some tests on Amazon services and some of Oracle services, but right now the interconnect, the stuff. I mean, we run on multiple nodes, and the interconnect between the different nodes is simply too slow. They all say, actually, they've been saying it for quite some years now, that it's going to happen soon.
Okay.
So right now we need to go to real supercomputers.
You use it in, what is the bottleneck? The analysis or the optimization?
It's always analysis. For everything we do, the optimization is less than 1%. So, and for the wing example, part of the iterative eigensolver. But if you go to harmonics, then you only have to get to the first eigenvalue. Beyond the first eigenvalue, then you are indefinite, meaning that all the preconditions fail. I mean, multigrid doesn't work. Algebraic multigrid hardly works. The generalized minimum residual, well, it does work, but it's really complicated. So there we have to do tricks. The trick to do harmonics is to project the solution to a very coarse space, and then do the actual solving the linear systems and getting the dynamics from that, and then projecting back to a fine space and don't solve and then push it on. So you can do something
by
like
doing
that.
that, you avoid localized nodes.
That as well, yeah. So that's an added benefit.
Because of the
Yeah.
coarse mesh.
Exactly. But actually, we are right now together with a colleague in China. We're actually testing the limits of what we can do with these geometric algebraic multi-grid preconditionals with respect to dynamics. And it's for solid mechanics, it seems to work quite, I would say, surprisingly well. For optics and high frequency acoustics, not the same. And so that's I think I have a paper, it's called like the pain of solving the Helmholtz problem. I mean, which is all about the indefiniteness. Yeah, but good question. Thanks.
Professor, we have a question at chat, YouTube chat. How can topology optimization be applied to dynamics topology optimization? Do you think non-gradient methods can also be used?
It can be applied to dynamics, and we do that regularly. I didn't include it here, but I work a lot in vibroacoustics, and we do large-scale models for hearing instruments. It actually was on the first slide, where we do some shape optimization. But I would put it like this: every optimization task requires its own tool. The SIMP method is good for something; it's not good for everything. And therefore, we use a combination of level sets and cut finite elements to do these kind of coupled physics problems, where you have nice geometry, you can impose it. And a comment about the genetic algorithms, I'm sorry to say so, but it's a no. I mean, it simply doesn't make sense to work with genetic algorithms unless you have a very small design space and your function evaluations takes a fraction of a millisecond. If you need to solve a PDE, I mean, you're gonna be a very old person before you get results. Yeah.
I have a question. Okay, so actually, in the design of the wing or even the bridge, you evaluate considering the mean compliance objective function, right? So, because usually what they do consider is stress as objective function, and if you like in the case of the wing, usually they like to consider, of course, also fluid surface interactions and like, for example, drag and lift in addition to, of course, I understand that.
Yeah, but not for the support structure.
Oh, I see.
Yes, we kept the aerodynamics out of it.
Okay,
Yes.
but anyway, so keeping the solid mechanics. So, like for example, what about if you consider stress?
Yeah.
You know what I mean? So how, because how optimal is the design when you compare to the 966 design, for example, when you consider stress? Because I imagine that's what they consider at the time. I don't know.
Yes, they're interested in that as well. Actually, the thing when we talked to both Boeing and Airbus afterwards, they were mostly concerned with lightning strikes. So very high temperature. So they would rather, the most important for them would be to couple it to a temperature model, which would be simple. Actually, I have some.
Sorry.
Today.
Eu vou tirar.
Yes, I think you need. No, so we can actually deal with that. We have a very nice way to incorporate stress constraints, and we can actually do it on ridiculous. I mean, more than up to 1 billion local constraints, while we ensure that if you under machine and over machine, you will get the same maximum stress. I have a few slides for you on this later.
Okay. Okay. So, Anna, we have to change now. So let's thank Professor Lewis again. Okay. So now it's my honor to announce our next speaker, Professor Casper Andersen, sorry, also from Technical University of Denmark. So,
Acho que o dele tá
Yes, sir.
Okay, so I'll give a presentation here called Lowering Carbon Footprint of Heat Transfer Devices.
Sorry. You need to share your presentation, please.
Yeah.
Sorry.
No. Yes, this is me. I'm from the same university as Niels, so in ETU in Denmark. So that's our nice green facility, but not as green as here in Sao Paulo. Yeah, so such as what you see here. So looking at whether raised or droop wingtips is a good idea, and also been continuing on the studies that Niels just showed, what actually happens if we include the aerodynamics. So here you see a smaller wing, but suddenly the wing shape is also allowed to change. And we've also been looking into these other sorts of methods where we can capture the interface much better. So we have some cut element optimization methods and then some other fluid methods here. But today I'm mostly be talking about heat transfer applications. So in a lot of components, there's a transport of heat, and the general idea on how to reduce the emissions is that you need to be better at transferring the heat. Maybe the computer will not produce less heat, but maybe if you are more efficient in removing the heat, you can also utilize more of the heat in a system that is coupled to this, or that you could fire in less fuel if you are better at converting heat streams in such a plate heat exchanger here or a shell and tube heat exchanger. So these will be some of the examples that I will come into here on how to try to apply topology optimization to these cases. So I'm also working on an industrial project together with some Danish companies and the Danish Technological Institute, which is a service provider that does AM printing and try to realize some of the ideas that we have on topology optimization. So here you see an example of what we could do. We could think of a shell and tube heat exchanger. It has only a few pipe bends, this shell and tube heat exchanger, but by applying topology optimization, we can get some complicated and high-performing heat exchanger. I'll come back to that, how that is working. But there's a lot of company interest, and the problem overall goal is to try to bring topology optimization to the industry such that they could facilitate lowering emissions by changing industrial products. But it's a tough task. So just a few words on the design representation. So here we will use this material distribution method that Niels also showed for the elastic designs, but there could also be options where it would be better to have an explicit boundary capture or something where you can actually cut through the elements, so some trimming procedure where you only need to consider what's inside. But the methods here of this kind of material distribution method where trying to model a nozzle, which would be outlined here by the red, is basically solved by having a porous medium approach. So for flow problems, we would motivate the topology optimization either by having a flow in between two parallel plates. However, that's not super generalizable to 3 dimensions. But one option could be to think about it as a mimicking of the different distance in between the two parallel plates, and then we could solve pipe bend problem like this and get, depending on the solution, a straight channel in case it was Stokes flow, or if you include some inertia, then you could also have a bend channel. So this is a classic result from the origin of the method back in 2003. I'd like to look at it in a bit different way, that if we would like to solve the flow problem in such a structure like this, we would think of a generalized porous medium approach. So you would basically either model it with a body-fitted method, right? But we are interested in trying to be able to modify these indents. So by filling in a porous medium, then we are able to mimic the flow domain and then introduce a solid medium that in which the fluid does not flow, or at least is very limited in its flow. So you could think of it as a generalized porous medium. Yeah, so you could use this, for instance, for optimizing an inertia-driven dosing unit, so basically a Venturi, that you would ask what would the design look like here if I would like to pull in some fluid from the bottom here, so it's on the left and then open on the right. So we are interested in how much can we actually get in of this secondary inlet here. And that's of course a sort of one problem that you will solve. Then in order to treat the problems in conjugate heat transfer, we also need to tackle thermal transport. And that's very similar to what you see in elasticity. So you would simply just consider a Poisson-like problem and then have a variable heat conductivity K here. There's also a volume constraint, and you see here by applying different filters, we get different solutions to this problem where we have a point that has temperature 0, and then we have an insulated boundary and a heat generating domain. So how do we most efficiently transport the heat away? And that's through some sort of tree-like structure. There's also been discussions on what the true optimal structure would look like, and for an infinite resolution, you will get a pinned structure, but you will not see that on a finite resolution. But we are able to combine these two, and the key to the success of the method is to treat the interpolation in between a low conductive medium and a high conductive medium. Just like for the flow, you would have a permeable and less permeable material. And then you can, of course, simply just introduce a convection problem and introduce the convection term here, and then you are suddenly able to treat the conjugate heat transfer. So that could look something like this. If you have a 2D heat sink model that you would like to let some fluid get in from this side and out here, and you have a heat generation in the domain, what should the structure look like? And we are able to optimize this whole structure. It gives some sort of meander-like curved channel here that has some conductors. And you can see, depending on the choice of parameters, you have success or no success with your method. So you could, since it's a model that relies on porous materials, you can have for certain choices of parameters, you can definitely have something that is not physically realizable, right? You have flow through the structure, you need to deal with that, or you could, by tweaking it differently, you could actually have the flow. So there are some challenges to the operator of the method to ensure that the physics are not viable. But I think today we have pretty good control of this, and it's well described in the literature how to deal with it. So then, stepping into more complicated three-dimensional problems, one problem could be to think about how can I mix cold and hot, for instance, in a mixer. So that was some of my earliest works, and you see that we can optimize something, but we can also try to do large-scale 3 dimensions here, and you will see that we have some basically cool and hot fluid coming in, and in the end we would like to have a uniform temperature profile. You can follow the, here it says concentration. You could think of it as either a concentration of a dilute suspension, or it could also just be the temperature as I'm motivating. And you could also see that there's definitely some stretching and folding going on here in this mixer. It's on a small scale, this, even though that the, so for a low Reynolds number, even though that it is a large scale resolution. So, or, you know, a very viscous fluid. Of course, for turbulent flow, it might mix all by itself, and then it's not so interesting. You could also make another question. Instead of just ensuring that you would like to mix, you could also try to look at the DTU logo here that has at the output, and yes, I can actually do that. So It could be some other things that you would like to mix or protrude or something in a production machine. So we definitely have control of what's going on. That brings us to trying to maximize the conjugate heat transfer. So, for instance, you could think of a cold plate for a water-cooled CPU. It looks something like this, has feature size 0.1 millimeters, extremely small fins. We try to optimize a full cold plate, but since that is really requiring a lot from the computer, then we first try to investigate 5 fins and then let the design change. So this is the problem, some inlet, some outlet, some heat input, and what is important is of course that the intensity of the heat input in the modern computer processor is quite high. We do the same tricks as before. We use this permeability approach here of Brinkman integration, so that simply adds an extra term to the Navier-Stokes equation, because some integration of the conductivity, and we will just let our first order gradient-based method free. There could be certain manufacturing conditions that we could be interested in. Of course, full design freedom, as you see to the left here, it could be very expensive to manufacture. Maybe by AM machining or in AM production methods, it's not so important, but it could also be that you would like to be able to mill it, so 2.5D designs, or maybe you could just want to have a 2D extruded design. Right? So we investigate different trade-offs between how well do we transfer the heat by the complexity of the design process and manufacturing process. So we look at the existing design, right? It has some simplicity to it, and we also investigated how does it look if we have full design freedom, and what about if it should be available like this. We can see that it is definitely a complex flow if we swipe through the finely detailed heats here, and we can see that there's a lot of second order flow going on in the convection process, trying to remove the heat from the bottom of it. By having this relatively thick conductive plate in the bottom, you ensure that you have stability of the heat sink, but you also make sure that you have a well distribution of the relatively intense heat input in the bottom. So typically you will have this sort of heat spreading effect in heat sinks. Yes. So what we see here is the ISO contours here from the density-based method. We have also done a post-evaluation where we actually extract the design and then remodel it using CFX. Yes, this was the final structure. We see that there are some differences in the way that design appears. Here we see some some snippets of the design history. How does the structure evolve? It's a little bit difficult to show it in 3 dimensions in comparison to 2D. Because if we have grayscale, we cannot see anything, but you see that organically the structure will appear from the bottom, of course, leading the heat away. We investigated some of the trade-offs here between doing different complexities in the design, and in general it seems to fit well. There are different ways. We definitely see that with, for instance, the extruded designs, if we look at the flow here, not much secondary flow is happening, right? And that's of course because you cannot really induce secondary motion. But with 2.5D design, you are actually able to create a landscape that can induce some secondary motion. So this one actually tends to perform pretty good. We can have a comparison study here of the reference that was just the fins. So it looks like here, and we see that it performs relatively good. The objective here is the mean temperature of the heat sink, so at different pressure drops. So it's actually pretty successful, the design that we already initially started at optimizing. And at the point we're optimizing somewhere over here, it's actually hard to beat it with the resolution we have available. But what we can optimize is the pressure drop, and that is also where we can gain from trying to lower in the emissions, that the pumping power that is needed to actually run the heat sink can be reduced by these methods that we present. It's difficult to bring down the average temperature, but we can maintain it at the same level at a lower pumping cost, so we also have a win. Yes. Then we could step into something that is a little bit more difficult, so a 2 fluids heat exchanger. So think about this design of the shell and tube heat exchanger, could also be something in a cross-flow heat exchanger. I'm not coming too much into that, but look at this one for now. So we made a design domain like this, and it, as a slide, or only looking at one half, it looks something like this in the initial configuration, considering oil, steel, and stainless steel and water on the other side. Then we try to optimize how this is working. In order to keep the phases separated, we need to have some sort of identification scheme. So we have an identification scheme where we have a single design variable by doing a filtering, projection, filtering, and then two different projections. We can get that either we have the blue phase, so one fluid, or the red phase, another fluid, and in between we would have the white phase, which would be the wall. So in this way, we can, with a single design variable, treat two different fluids and one solid. And it consists of some known tricks in the, or known methodology in the literature. So I'll not go further into that. So, but it's a PE filter and some projection. So, yeah. So that means basically this would be the design field. We make an interface representation of this wall, and then we subtract the two and see that we have two different phases here, side 1 and 2, and then we can actually prescribe the wall thickness here in between, so we can have multiple elements with thickness. So the real question is, can we optimize the heat transfer in this counterflow heat exchanger? For instance, or we could also be the shell and tube heat exchanger here shown. So we are interested in how much enthalpy do we transfer from one side to the other. And we can see here in the design history, I guess we can see it. No? Yeah, so you can see that it is evolving, right? And we have these small wheels that are appearing on the surface to try to diffuse more heat into the surrounding fluid. Yeah, we can see an image, some visualization of this exchange, and we definitely see that the wheels are intercoupled, which will mean that there will be a relatively high heat exchange in between. So there's of course some dependence on what you choose as an initial design and how you progress in the optimization, so you can get different variations of the design depending on the conditions. Yeah, so we also did some studies here on the design details, but in general, we could increase the heat transfer by 113% at the same operational cost. So we definitely showed that we can optimize the heat transfer in lowering the pressure levels. We could also look at what happens if it has lower solid conductivity. So what if it was made in plastic instead of steel, for instance? Then we don't see these entanglements into the domain because diffusion is not so dominating. And if we increase the wall thickness, then of course more of the resistance in the heat transfer is neutral. Yeah, we tried another application. It could be a cross-flow heat exchanger. We can definitely get some intricate designs, and we could also see here that we have a certain wall thickness. Here, so we could see the streamlines. So we see the streamlines on the top part, that it's really an entangled geometry, and the wall interface area is really maximized during this procedure. Yes. Then the final slide, because all of this, solving all these Navier-Stokes equations for two domains and also the heat exchange is quite an expensive process and requires large computers. So we have also done some efforts in order to try to lower the computational burden, because for many problems here it's showcased in a natural convection problem. Then a lot of it is just trying to mimic how is the fluid actually moving. And that can, to some extent, be done by using a potential flow solution instead of solving the full Navier-Stokes equation. So we have tried to bring down the simulation cost here from like a whole day to 1 hour on a 3D case, simply just by solving a potential flow instead of the full Navier-Stokes equations. And that basically means that it's a Darcy flow-like problem that you solve, and then you of course need to do some post-evaluation, but you have reasonably good performance of your designs, and then you could maybe do a few full Navier-Stokes solutions in the end to get the fine-tuning ready. But just by using this low-cost methodology, you can actually get way better designs than by engineering intuition. So I think this concludes the presentation here, that there's a huge potential to try to reduce energy consumption and increase the efficiency of these heat transfer devices. Yes, thank you.
Okay, so thank you. Let's open for questions.
I have a question. For the filter used in the interface problem between the two fluids and solid, is it difficult to plan the parameters to?
No, it's actually pretty well defined how these parameters are in the reference that was given here. So in this reference here, the original paper by Lou, that's a pretty good estimation of what should these numbers be. You see, I've given something about what should the difference between the two projections be, what should, and it's a certain distance between the projections, you can actually show that you get for a sufficient high beta, that you will get water size of a certain size. So it's not totally random what comes out. It's pretty well documented. But of course, you rely on the fact that this will be eventually a very steep projection. So you will continuate this beta parameter while running, maybe not starting from 0 or 1, but you need to ramp it a little bit.
And for example, are the betas equal for the two projections?
Yeah, we just use the same one. So over here, I'm trying to show what happens when I increase beta, right? And you see when beta increases, it gets better and better at making this water representation. So you see if beta is 1, right, you don't really have a nice water, but already at 8, you seem to have the good representation, or the possibility of having a good representation, right? If the design level of the field is, of course, just great, then it's different.
And is it necessary to make calculation on the material model too, or?
Yeah, definitely. Yeah, but it's a tricky interplay, right? Because suddenly the physics might change a lot. But it's one way to try to tackle multi-material models with a single design field.
I have a question. Oh,
Have you already run any experimental tests with the geometries obtained?
We have so far only tried to manufacture the heatsink for we're trying to manufacture the heatsink and actually also the heat exchanger, but it has not been tested in any rigorous way because there's some limitations to the. So of course the heat exchanger might be nice if it was in copper, but the methods for producing AM or for making additive manufactured copper specimens is a little bit tricky. Typically it's binder jetting and then very small scale production.
That's what I was thinking. Like it's really hard to make them to manufacture this solution. So I was asking.
But we did not do any of those. But I mean, in the literature, there's a lot of tests where people monitor with an IR. Yeah. But to my knowledge, many of the optimized structures they don't have a very large pressure drop that is comparable to what you have in industrial applications. And when you have large pressure drops, it seems to be more challenging to get good results. But I haven't tested myself, so it's a bit hard to say whether that would make a large change in experiments.
We have a question on YouTube. Murilo said, "Nice presentation, Professor. Could you comment about the turbulence models utilized for the viscous case?
Yeah.
Were his results validated or compared with other software?"
Yeah. So we treated for the heatsink situations where it's not in the turbulent regime. so there was no turbulence model. But it would be a natural extension to the model to include some turbulence model. Definitely relevant. But for instance, for the heat transfer in heat sinks for computers, for instance, you're not interested in having turbulence because then the flow and the pressure drop relation changes to something that is not as advantageous as for the linear relation between the flow and pump pressure. So they would actually like to keep it laminar if you can, but the efforts to trying to keep laminar in difficult geometries could be something.
Okay, so I have a question, actually three questions. First one is, so congratulations for the presentation. And okay, so we know that when we do topology optimization for fluids, we have the issue of fluid penetrating into the socket. Okay, so how you deal with that here? How difficult it is? I mean, how?
Yeah. So we increase the impermeability.
Yeah, but sometimes not enough.
Yeah. But we monitor how far to go, right? And then we increase even more.
Because then you get some instability.
Yeah. So you might end up in troubles. But so far we have done the post evaluation to check if it's ramping up the impermeability during the optimization. Then in the end do a post evaluation if it's a problem or not. But of course there could be some automated methods to try to do that. Definitely something that you need to pay attention to.
Okay, the second question is, like you guys asked me also yesterday about this topology optimization, shape optimization, right? So in the feed design, right? So you made the topology optimization, but at the end you have to move to a kind of shape optimization solution. So, I mean, how do you see? I mean, I work with topology optimization fluids, and people keep asking about, because sometimes, you know, if you have these floating structures, they are quite difficult to implement. So how do you see, in your opinion, this issue, topology versus shape for fluids?
Yeah, if you were very interested in the what's happening in the interface, and we would be in many cases right for fluid structure interaction or some multi-phase flow or other conditions, right? Then if you're very interested in those, then maybe some method that is well representing the interface would be better than these. However, typically they have difficulty in making large mobility in the design process, right? So therefore, I see a more reasonable way to do it is to try to work on the topology first, and then do a few sweeps of the shape optimization, or find a method that can do both, right? But,
so large mobility is the issue.
Yeah, I think this. Yeah. So for many explicit bandwidth capture methods, it's difficult to move over large distances.
And third question is regarding the last. I found curious about the last slide about the potential flow solution.
Yeah.
So my curiosity here is like, okay, so suppose that you are solving a Stokes. Okay, now the Stokes, let's say laminar flow. Okay, so we have viscosity. So what we're suggesting here is that we could start solving a potential solution has no viscosity. Okay, so it's a kind of I mean, it's an initial guess, a different way of making initial guess. And that's my question. So
yeah, you could also phrase it that way. That it's better than intuition.
I see.
Initial guess could be right. But of course, there might be cases where exactly the neglection of internal friction is key to how it will function, right? So maybe it would have many small branches, which is not a problem for potential modeling, but would be a problem for viscous fluid.
okay.
So definitely there's some trade-off there on how to do it. It's a bit tricky, but I mean, if you can progress far, and then maybe you get something that is better than what you had initially at a low cost. I think we need to consider how to get low cost.
Thank you. Yeah, sure. Yeah, that's an issue for sure. Yeah. So more questions?
I have a question. You mentioned the cut method. Did you use it with the density-based optimization or with the site?
No, with the density. So the slide that I showed here is with the density method ingredients, I would say, but basically the thing is that the two is almost the same. So yeah, where is it? It's here. So this method that we have here is basically, you could say, a density field. So in every node there is a level set value or density value, and then we simply just use the filtering and prediction scheme that we know from density-based methods, and then that is used to cut the elements in here, and then that is what you see. So,
And how do you calculate the sensitivity on an element that is?
So for the individual element, you would do a semi-analytical perturbation strategy, right? So for instance, in 2D there would be 4 nodes, so you just need to perturb at least 3 nodes, right, in order to find the sensitivity. And since the interface is not covering a large portion, then it's not so critical. But you could of course also just differentiate, but I mean, then you need to differentiate at each Gauss point, for instance, that adds up. Yeah.
Okay, so more questions? No? Okay, so let's thank Professor Casper again. So I believe that the end of our colloquium. I thank the audience, and I hope to see you guys again here in the 11th RCGI Collouium. Okay, bye-bye.